Hey everybody, Dr. White here again. I promised to do a couple more examples of transformations when you're in the bivariate situation. So, how about exercise number 1 in the section? So, say that x1 and x2 are independent and they're both distributed like chi-square random variable with r equals 2 degrees freedom. And let's let y1 be x1, and let's let y2 be x1 plus x2. This is something that you might do if you were curious to know what's the sum of two independent chi-squares, each of which has 2 degrees freedom. What's it distributed like? And you would maybe just introduce this other transformation because you were thinking ahead about back solving and saw that that might be a convenient other variable to pair with. So here we are moving to this new bivariate situation, y1, y2. So we need to first figure out what's the joint PDF for the x1, x2 situation. Well, we don't usually memorize the PDF for chi-squares. We just remember that there's specializations of gammas where the alpha parameter is r over 2 and the theta parameter is 2. So from that, we can get 1 over the gamma, the alpha. We have the theta parameter to the alpha. We have your x variable to the alpha minus 1, and you have e to the minus x over the theta. And so that's going to be true for the little x1 and little x2, no matter which one you're working with. And that kind of simplifies a lot. In fact, all you're going to get out of that initial fraction is a 1/2. And this little guy here is going to turn out to be, xi to the 0, 1. So for either x1 or x2, the support is 0 to infinity, and there's the PDF for the individual random variable. So when I stare at that, I realize, whoa, that's the PDF, same support, for an exponential random variable where the theta is 2. So a chi-square with 2 degrees freedom really is just an exponential random variable all along. Okay. Now, because the x1 and x2 are independent, you can easily write down the joint PDF for x1, x2 is just the product of those PDFs, pa-bump, which I'll combine that way. And the x1 and x2 are allowed to be anything between 0 and infinity. So the support is the first quadrant of R2. Okay, let's see if we can find the joint PDF for the y1, y2. So for that, we're going to need to back solve. So let me write down my original transformations here and back solve. So x1 is pretty darn easy to find. It's just y1. And x2 is pretty easy to find. It's y2 minus x1, but we just found x1 is y1, so it's y2 minus 1. So I've got my new 1, and I've got my new 2. And so I can go and grab their partial derivatives, and they turn out to be these things here, these numbers this time. Then the determinant is 1 times 1 minus 0 times negative 1, which is just a 1. The absolute value of it is a 1. So the Jacobian's a 1, and the absolute value of the Jacobian is also a 1. I shouldn't have stuck the absolute value in there at the end. I should have stuck it right here. So I am going to make that change. Change made. Okay. Now, so I just got to plug in f at the x's, but I express them in terms of my y's. And so I'm going to plug in y1 and a y2 minus a y1 instead of an x1 and an x2. And so remember, it was 1/4 e to the negative x1 plus x2. So I'm doing a y1 plus a y2 minus y1. So there's a little cancellation there. And I'm just going to end up with 1/4 e to the negative y2 over 2, which is kind of interesting. It's like it doesn't matter what y1 is anymore. So what's the support? Well, thinking about what y1 and y2 were, how they were defined, which is here, you'll notice that the y1 has to be less than the y2 because the y2 is the y1 plus an x2, which is got to be a positive thing because chi-squareds are positive. So I'm left with this as a support. So it's just that upper triangle that we often see in problems like this. So now we can get the marginals for y1 and for y2. Now we're interested mostly in the marginal for y2 because that's the the mysterious sum of the independent chi-squares. But I'm just going to go ahead and get both marginals just for fun. So thinking about trying to get y1. Now, in a way, we already know the answer because y1 is x1, and we know that x1 is a chi-square with 2 degrees of freedom, which is the same as an exponential with theta parameter 2. But let's at least see if we can verify that by getting the marginal off of the joint, making sure we can do the math. So I'll call the marginal g sub y1. And at any possible value little y1, by definition, it's integrate over the real line, the joint, dy2. Now remember, y2 is at least y1 on the support, so I only have to go y1 to infinity. So I've got this integral to do. That's not a hard integral to do, but I'm so insistent on being cool that I see if I can relate it to a probability fact. So I'm pulling a factor of a half outside here, and I'm staring at that and realizing that's the PDF for an exponential theta equals 2. And to emphasize that fact, I'm going to change the dummy variable from a y2 to just an x. Okay. So here I am integrating from y1 to infinity, so I'm asking for the probability that an exponential with theta parameter 2 is bigger than or equal to y1. And hey, we know the cute fact about exponentials is the chance they're bigger than the number is e to the minus number over the theta. So I've got a half e to the minus y1 over 2. So that's the PDF for y1. That works for all y1s in the support. Whoa, that's the PDF for an exponential with theta parameter 2, like we had to have. Okay, now for y2, which is more interesting. Intuitively, we expect, since it's the sum of independent exponentials, that it should be a gamma, because each exponential is like the waiting time for the first event in a Poisson process. So it's like wait for the first event and then wait for the next event and add those two times together. It should be like, this should come out to be a gamma, where the alpha is a 2 and the theta is still a 2. But let's verify it. And this will be our first rigorous definition that the sum of independent exponential thetas really is a gamma. Let's verify this by going from the joint to the marginal. So I'll call the marginal g sub y2, and I'm going to find it at any possible little y2. So I got to integrate the joint with respect to y1. Okay, so thinking about your support, which is this upper triangle, and I'm wondering about, like, I've got any y2 here, and I've got to integrate over all the y1s. Well, the possible y1s where the g is like more than 0 would only be the y1s that take you from here to here. And it's like at this point, the y1 is a 0. And up here, the y1 and the y2 are the same because you're on the y1 equals y2 line. So your y1s, you really only need to integrate from 0 to y2. And so you look at this integral, and it's an integral with respect to y1, so actually all that mess in there is a constant. I can just factor it out. And you're integrating 1 from 0 to y2, which is just the area of a rectangle whose base is y2 long and whose height is 1. And so its area is just y2. And so stick that y2 in a nice place and kind of stare at it, and you realize, power of variable e2 minus the variable, that's like a gamma. So I'm going to make that fit just right. I'm going to write y2 to the 1 here as y2 to the 2 minus 1, and put a 1 over gamma 2 squared here, and it's going to like totally fit. That's the PDF for a gamma random variable where the shape parameter alpha is a 2 and the theta is a 2. Wow, this is great. Okay, so we use the change of variables technique again for that one. I need to do like a CDF technique sometime. So let me try number 13. So in number 13, you've got yourself two exponential theta random variables, and they're independent of each other. And just for excitement, let's use it to model some real life situation. Say you got a machine that has two components, okay? And I'll call it machine one. And machine one has these two components, and each of them has a lifetime that's exponentially distributed. And both the components have to be working for the machine to work. So as soon as the first one fails, the machine breaks. Let's let capital Y1 be the lifetime of this machine one. Okay, so that would be the minimum value of x1 and x2, right? Because you're going to fail as soon as one of them fails. So the first one that fails, the minimum of the two, that will determine the lifespan. Okay, let's imagine another machine where it can actually continue. It has two components, okay? And they're both exponentially distributed and they're independent of each other. But the machine can continue to function as long as at least one of the components is working. So for it to die, both the components have to die. So that means its lifetime, which I call Y2, would be the maximum of those two variables. And let's just see if we can get their distributions. Okay. So this one's not a really good candidate for trying to do back solving on, you know? And I don't even know if there's like one-to-oneness that's going to be involved or anything like that. There's certainly no like calculus where you can take derivatives of anything. So not a good time for change of variables, but we might be able to use the CDF technique. So let's go for the CDF of capital Y1 at any possible little y1. So we're looking for the probability that capital Y1 is less than or equal to little y1. What's the probability that the minimum of those two variables, x1 and x2, is less than or equal to y1? And it looks like I might have left out an x1. It's got the comma there, but not the x1. So let me add that in. Okay. Well, I'm going to write that as 1 minus the probability that the minimum is bigger than y1. Because for the minimum to be bigger than y1, that's easily expressible as saying that x1 has to be bigger than y1 and x2 has to be bigger than y1. And remember, x1 and x2 are independent. So this probability of an and, I can just get it by multiplying the probabilities together. And they're exponential random variables. The chance for being bigger than a number is that easy to remember fact. The first chance is e to the minus y1 over its theta, and the second one is e to the minus y1 over its theta. So if we use property of exponents, that can combine into that. Now, I can further, kind of perversely, write that as dividing by a theta over 2 instead of multiplying by a 2 and dividing by theta. And I do that because when I stare at that, I realize, wait a minute, that's the CDF function for an exponential random variable with parameter theta over 2. So what I've just found is that the minimum of 2 independent exponential thetas is also exponential theta, but with half the expected value, which kind of makes sense, but it's still cool. So now let's investigate y2, which is the maximum. And so, we're looking for its CDF. We're looking for the chance that the max is less than or equal to y2. We're looking for the probability of that intersection, which is the product of these probabilities, which by the formulas for the CDFs of exponentials is these things. So it's two things that are the same, multiply them together, you get the square. And so it's that on this support. And that doesn't look really familiar to me, so I don't know of it as some kind of like already known important distribution, but it's there. We found it with the CDF technique. So actually the CDF technique can feel a little bit easier to apply, even if you have to do some calculus on it sometime. It's often a little easier to apply than the change of variables technique. So don't hesitate to look around for opportunities to use it. That's all I got for now. I think we might do some R work to just look into see the beta distribution. We wanted to investigate that a bit, and also those F distributions that we learned about in the previous screencast too. See ya soon.